All right, you should be good to go.
Cool. Thanks, Mia. Welcome back to another VCLibs video code review. So today we will be looking at a new PR from Adam Bussior called More Optimizations for Contiguous Iterators. The background here is we had recently merged a PR from Adam. You can actually see that in our history, where he went and extended an optimization that we had, or a set of optimizations that we had for a long time in various STL algorithms. These optimizations now detect arbitrary contiguous iterators because Adam improved the metaprogramming there. And he also extended it to the recently implemented ranges algorithms. So although we've been focusing on finishing CS+20 features, we prioritized this review because it made ranges better, and ranges will be available in VS 2019-1610 preview 2. I was about to say VS 2010 there, but that is not the right release. So we have another PR from Adam, and this seems like a good candidate to review, so we'll take a look at it. The idea around the optimizations here is that, in theory, one could imagine a world where we just wrote extremely natural code in the STL, like copy could just iterate through each element and write elements to the output range. Same for move, the move algorithm. Things like reverse would just do the natural loops, and then we could rely on the compiler backend to detect common patterns and emit more efficient code gen for them. Because in theory, if you are just iterating through something like a vector or built-in array with raw pointers, and you're just copying ints or bytes, in theory, the compiler could look at that and say, hey, I don't actually need to be copying 4 or 8 bytes at a time. I could just transform this into a single mem copy or mem move, depending on the semantics, or mem set for std fill, memchure for std find. You could imagine a world where that happens, and according to my understanding, the various compiler backends do have some such optimizations. However, because we love template metaprogramming so much, we have historically had logic that will detect things like, okay, you're copying between raw pointers and the pointed to elements are trivially copyable, which we've extended over the years. Originally, we only detected scalars like int. Now we'll detect arbitrary, trivially copyable types. And we will intercept that at compile time and emit a call to the CRT function that's best suited for, memmove, memset, memchure, things like that. So this achieves a couple things. One, it makes the compiler backend work less hard, which is always nice. We don't need to, hope that it's going to detect the pattern. We can just apply it. And in some cases, we may be able to see with this template metaprogramming cases where it's safe, where due to aliasing or whatever reason, the backend might not be 100% sure. The other major thing that this buys us is performance in non-optimized debug mode. Because in debug mode, the optimizer isn't even running. We're not even getting any inline. Any inlining. Every function call in the source code is a real function call. Pushing arguments onto the stack and then popping and all that. And so having to iterate through and copy ints one at a time when we could just directly call mem copy, mem move. And have that emit ultra optimized assembly that's sometimes specific per processor to be very friendly to them. That will help debug mode, which is nice because if your program is undebuggably slow, that's a problem. So that's why we continue to retain these optimizations, and in fact, it's getting easier over time because we now have machine read-like concepts that allows us to detect arbitrary contiguous iterators, which is something that's not available in the classic iterator hierarchy of strengths. We could detect random access iterators, but not quite if you were an arbitrary contiguous iterator. We could detect raw pointers. But what if you're some special container that has contiguous storage but provides user-defined iterators? We couldn't sense that. Now with concepts, we can have an iterator concept, I believe it is, that tags itself as contiguous iterator, so it satisfies the contiguous iterator concept. And Since we also have access now to ifconst_expr, we don't need to use tag dispatch, which was a real headache. Now we can write code more easily, also variable templates. So metaprogramming is getting easier, and we're going to use this newfound power in different ways, and that's what Adam is doing here. So let's read through a summary before we look at the code. I have not looked at the code yet, but Casey has. So Adam is implementing the memmove optimization, which handles, this is a bit of confusing terminology. The CRT has memcopy and memmove, and the distinction is that memmove handles arbitrary overlapping ranges. This is very different from the standard where the copy and move algorithms refer to, move semantics. So memmove, because it handles arbitrary overlapping ranges, is the one that we want. If you look at the specification of the classic std copy, it actually permits overlapping in one direction, but not the other. It's the direction that would naturally work if you did a front to back copy in order. So because it could be overlapping a little bit, we need to use memmove. In practice, there's no actual distinction. They both have the same performance. And in fact, I believe our implementation of memcopy always calls memmove because people aren't strict about always calling it for non-overlapping ranges. You shouldn't rely on that, but that's apparently what we do. It is correct to call memmove here this, so it's nice to see that. And then Adam is extending the memcopy optimization to the ranges uninitialized algorithms for non-common ranges. I believe this is the terminology where a range's iterator and sentinel, which marks the end, are not the same type. This is an advanced thing in ranges where you could imagine, some iterators know their own bounds. Some iterators are potentially generating like an infinite range, or some iterators they might not know their own bounds, but they'll know it when they see it. Like if you have a special iterator over a null terminated string, you don't know its size immediately, but as you iterate through, if you encounter a null character, you can stop. So this was previously not really expressible in the classic STL that required iterators to always be of the same type. Couldn't even handle, mixing iterator and const iterator due to template argument deduction. And now with ranges, you can have differing sentinel types. So Adam's extending that. That one can be memcopy because if we're doing a copy or a move to uninitialized memory, that had better not overlap with the source. That would be very bad. Let's see, doing nothing for trivially destructible types optimization and ranges destroy. That's another one where the backend does optimize that away. Like if you try to destroy an int with p arrow ddor t syntax, the backend will optimize that away, but only in release mode. In debug mode, you pay a cost there, and it's faster to just skip that. Optimizations for non-unwrappable contiguous iterators, and everything depends on putter copycat and putter movecat. So unwrapping is an internal STL idea where if we have something like a vector iterator, we can just unwrap that to a raw pointer after doing checking to make sure that the iterators aren't reversed, things like that. We can even take these days things like list iterators and unwrap them so that they don't perform checking that they're valid when you dereference and increment them, because we're pretty confident that STL algorithms will not do bad things like run over bounds with iterators. So we'd like to pay any checking costs upfront and then unwrap for maximum speed as much as possible. And then Adam is enhancing putter copycat for move iterators, which will ask, okay, is it safe to move the elements? That makes sense too. Okay, so let's see what is changing. Only 133 lines added, 82 removed, so relatively small PR. Okay, so we are in algorithm ranges. What is this? We are implementing ranges copy. So this is the internal helper copy unchecked. Oh, this might be a little small. I am not zoomed at 125. Actually, I may have been using the same size before, but this is more readable anyways. Okay. Okay, so this is signature is changing a little bit. Last is no longer const. Why is that? Because we are going to move it, and moving from a const sentinel could be inefficient. So we should mark that as non-const. Okay, that's good. We now have a early check here for if we can do cool optimization, do so. So the way we structure this is first we see, are we eligible at compile time for this optimization? We're implementing a ranges copy. So we're going to ask putter copycat, which returns the copy category for a pointer, hopefully a pointer. It's been, because the optimization has been extended, this is no longer very accurate naming, but this is the classic name, so we're going to keep it. For the iterator for the source and the output iterator, if this thing tells us that we're trivially copyable, which is, this maps to the standard type trait of trivially copyable, basically. And if the sentinel is a sized sentinel for the iterator, meaning that we can subtract it in a single step to get how many elements there are, then even if these things are different types, if this type trait says, hey, this stuff is contiguous, the element is eligible, and we can tell you how many they are, that is the criteria for us to activate the optimization. But wait, we can't quite activate it because this is a const_expr algorithm. And if we try to call the CRT function memMove, that is thoroughly not const_expr. It's full of assembly code. So we cannot activate this optimization if we're being asked to perform const_expr evaluation. So that's where we can use the function stood is constant evaluated, and we'll activate this only if we are not constant evaluated, meaning we're at runtime. Then we can do cool thing and return. So the logic here is if we are not eligible at compile time at all, don't even consider any of this stuff, do the classic loop. If we are eligible, but we're under constant evaluation, this would fail to compile, so we can't do this early return, and we need to do this for loop. Testing is constant evaluated must always be done with a plain if, not an if const_expr, because if const_expr is constant evaluated would force that to be true. You just asked it, hey, at compile time, are you constant evaluated? So that's why this needs to be runtime, and there's a compiler warning specifically for that accidental misuse. So if that's the case, we are going to get the end of the range, but because the sentinel is called class, we need a different name for it. So we're going to call it final. We're going to use ranges next to create a copy of first that is advanced by all the way up to last. So this handles the cases of if they're the same type, then just return last basically. Otherwise, if it's size sentinel, then add, use plus equal. So all that logic has been handled for us. This is our only use of last, so we can just move it for efficiency. And we have that stored in final. We are eventually going to move from it, so that's why it's not const. Then we're going to call our copy memMove helper, which handles the logic of let's convert elements, number of elements into, or range of elements into a count of bytes for memMove. So memMove is correct because these could be overlapping. And we're going to move in the first iterator, pass final, and then move the result iterator. Okay. Result output iterator, and then assign that back to result, and then move both final and result as the returned values. That all looks correct. Yep, because we need to return the fully incremented input. That's what final is, and then the output. Okay, so this is all correct. This is great. And this will hopefully lead to more efficient code gen in debug mode, and occasionally in release mode when we can detect this optimization, but the backend isn't fully convinced. Okay, onward. We have similar code here for ranges copy n, a little bit different because it takes an iter difference to it count. So first thing we do is we unwrap the input first. This is not necessary in copy unchecked because the stuff outside copy unchecked will already have unwrapped. Here we get to assume it's unwrapped. Here we are directly the user-facing operator pren, so we need to perform the unwrapping first. And then we can start asking the compile time question. If const_expr putter copycat, and we are a copy algorithm, the input is the declared type of uFirst, which is non-const, that's good. And the output iterator, if that's trivially copyable, we're eligible, yep. And then if at runtime, we are not constant evaluated, we can do cool thing and early return, same pattern. Here we can have the final iterator, and we're going to need to use uFirst, so we can't move from it here. We're just going to say uFirst plus count. We can do this because we know that although at this level in the operator, it is only known to be an input iterator. After we've if const x tested that it is eligible for the optimization, we know it's actually contiguous. We can go all the way to operator plus. So u first plus the count will give us the final. We will call copy memmove, again, memmove to handle overlapping ranges. Move in the u first, pass final there, move in the result, assign back to result, yep. Then, because first is the original potentially wrapped iterator, meaning the potential user-defined type that's not a raw pointer, we need to essentially set it to where the raw pointer, hopefully final, actually definitely final, points to. This will handle the case where if this, oh, that's an interesting. Oh, copy memmove internally now handles the case where if you give it a wrapped contiguous iterator, it will unwrap to a raw pointer, because you can always do that if you dereference and then take its address, even if the iterator doesn't otherwise provide unwrapping. So we don't need to worry about, oh, what if this was a unwrap or a still user-defined wrapped iterator. But in the case that we did unwrap, for example, from a vector iterator to a raw pointer, the user needs to see a vector iterator. We can't just hand them back a raw pointer. So that's what seek-wrap does. This is a STL helper that will advance first to where final is in constant time because it's random access. And yep, that's the last use of final. And then we can return move first, which is the original type, and then move result. Okay, that's great. And then classic loop, that's all right. Next up, we've got ranges move. Okay, so drop const on the sentinel because we need to move from it. Yep. Then check if we're eligible for the optimization. Now we need the putter move cat because this is a move algorithm. If we're trivially copyable, but we are not constant evaluated, then do cool optimization. So we're going to use ranges next to advanced first. Still need to move from it all the way up to last. We can move from that now. That's final. Call copy memmove to handle overlapping ranges. Nothing to do with that move there. Move the first, yep, pass final, and then move result, sign back, and then move final and result. Yes, this is great. And that's it for algorithm. Okay, let's look at memory. This looks like the uninitialized algorithms because the standard loves algorithms so much it defines them in more than just the algorithm header. So this is, let me find the comment, ranges uninitialized copy, operator prime prime. So here we are handling potentially checked iterators, but the stuff in the operator prime prime will handle unwrapping and eventually call uninitialized copy unchecked, internal helper. This is so that the various like takes iterators versus takes ranges algorithms don't have to duplicate their implementations. So all this stuff has been unwrapped. We got some static certs saying that we actually do satisfy all the concepts. These will vanish because they're STL internal when we're in user code. Okay, so this is interesting. There is no move semantics for the sentinels. So the sentinels remain const. It's a difference from the other algorithm. I wonder if the constants here would be desirable to remove. So we could say ranges next, I first stood move I last. Because we were doing that before in algorithm. We were doing, let me find it. Ranges next, first, move last, where last is the sentinel. If this is the final use of the sentinel, it would seem reasonable to move it, which might make a difference. Probably not. Like most of the time, it doesn't make a difference for such sentinels. Here we are. We do move O first when possible. In fact, I wonder if, well, I first is referred twice, but I last, O first, and O last. These are all mentioned once.
O first is twice on that line.
Oh, you're correct. Yes. Now I wonder if it actually matters.
O last I missed. Yeah, I missed that this one could be moved. I pointed the other ones out on my review. So.
Ah, cool. Yay, I found something. I assume it does make I assume it does make a difference potentially for some interesting user-defined iterators, even though here we know we're eligible for the optimization and we're going to convert it to a raw pointer as soon as possible. It could still make a difference.
Yeah, in theory.
Okay, in theory. And so it seems like we should do that for consistency. Okay, I will add a comment. Hooray. It would be on this line. Let's see, what are the ones that aren't mentioned twice? It's only the last ones. I first, or I last, last. These are the only uses of I last and O last. Let's see. For consistency, I believe they should be non-const and then moved here. Cool. Okay, so let's see if the metaprogramming is correct. If const expr, we are doing an uninitialized copy, so put our copycat, given the it and the out. We're really trivial. We also need to check the sentinels because we need to know how many elements there are. C has to be a size sentinel for the iterator, and OC needs to be a size sentinel for the output iterator. Yep, that's all correct. Then we can return copy, because it's uninitialized copy, mem copy common, and it's mem copy because for the uninitialized copy, there's no way those things should be overlapping. Okay, that's all good. So as long as we've got the move, we're good there. And we don't need to worry about exception back out because we can just do it in a single function call. No failure. Okay, now destroy. That's interesting that we don't have anything for uninitialized move. Does that live somewhere else? Yes, it does. Okay. Okay, destroy. Okay, so this is destroy unchecked, which is a helper. Previously, we always did a loop with no optimizations. Now we're going to do an optimization. So if const expr is trivially destructible v, meaning the destructor has nothing to do. And we're going to ask this about the value type of the iterator. Yep. Then, since there's nothing to do, we can just skip all the way to the end. Range is advanced first, all the way to last. Same question in my mind about whether that should be a move. Sure seems like it. And then otherwise, classic loop has just been indented here. Okay. Let's see. This really does seem like it should be a move because if they happen to be the same type, I believe ranges advanced will say, hey, I can just assign this. And then that would move assign all the way to first. I'm not hearing disagreement from Casey, so I think my analysis is correct.
I concur. Sorry, I didn't know if you were wanting me to back you up there or not. But yeah,
that sounds good. I'm still learning ranges. I'm getting increasingly confident in my assessments, but you still know like a zillion times more than I do. So I do appreciate the confirmation. Thank you. Like I know how classic iterators work, but then C++ went and changed all the rules on me, so I got to learn like a whole new language. Okay, so here, or this is the final use of last. So it should be non-const and then moved from, which will make a difference. And yeah, I don't need to say that it's where. It's the right thing to do. Okay, this is the final use of last, so it should be non-const and then move from. Okay, good. And that's it for memory. XMemory. Okay, so we've got some changes here. Inserting I first and I last putter. Oh, and it's showing up because it's being renamed. Okay, so it looks like a lot of logic changes, but I don't think it's actually that bad. Previously, and I think this was actually called out in the conversation, that we're now handling cases where we can't just directly This was assuming, oh, you've got something that's a pointer, so we just need to convert you through reinterpretation to char, but now we need to handle arbitrary iterators, which indeed was the signature here. So we have a helper function called toAddress that'll do that. So now iFirstPutter is toAddress iFirst. Yep. Looking for any copy paste errors. Those are always tempting. And then once we've got raw pointers, they may not have the right type. They could be, unsigned char or something. Or int, pointer to int, because this is memcopy. We can handle things larger than a byte. So we need to reinterpret all the way to char, but we got to respect constants while doing so, because CCasts are super evil. So we reinterpret all the way up to const volatile char star, which adds CV qualifiers potentially. That's always fine to do. And then const cast away down to char star. The last ones we don't write through, so those can be const char star. And then what is going on here? Why is there no const here? Obviously, the output iterator we need to be able to write through. So it may, if this thing were a pointer to const, we would already be doomed. So there's no reason to try to add const and then remove it. But pretty sure, because you can't write to const.
In all of the uninitialized algorithms now, right? They're specified in terms of voidify.
Yeah, but here we know they're raw pointers, so we can do whatever we want. Like toAddress is taking care of that.
Yeah, but that might be a pointer to const is what I'm trying to say.
But if it's the output iterator, how could it possibly be a pointer to const? Like we're writing to an output range. If the user gave us pointer to const, it should totally fail to compile.
No, that's not the case.
Really? Why is that?
Due to the use of voidify in the spec, right? If you want to create a sequence of const objects and you pass this as pointer to const type, then that's what we do. We make a sequence of const objects.
That is so weird. Okay.
It's very weird.
The language has changed.
Billy hated it, just adamantly opposed it. I honestly didn't care a whole lot. It felt general to me that we could create const objects as well as non-const objects. Luke argued over it like 3 or 4 different times and decided to leave it the way it is in the working graph. But yeah, they're all specified in terms of an exposition-only helper function, voidify. Placement new, past voidify of something.
Yep.
Ta-da! And voidify does the magic to convert address.
Oh, look at that! It takes away the constness. Interesting. I thought that was just a cleanup. I didn't realize it was actually a big thing of debate that has this effect. Okay.
The initial uses of voidify were special and novel and completely bizarre. The follow-on of, well, let's use it everywhere uniformly was kind of a cleanup.
Yeah. Okay. Interesting. I learned something. Thank you.
So these probably should be potentially const stripping, just like the inputs are.
Yeah, in fact, that's what we did for the input. Like the input, even though the input, we could just say, oh, we're just always going to add const. We're never going to, modify it. This was actually adding the const and then removing it. It's just we're skipping it here. So I think to restore correctness, this just needs to be const volatile char star, and then we're okay. Because all these would add CV, and then I still don't understand what's going on with the first. Why isn't the first const? But this one would then be non-const. So what is going on with iFirst? I could have sworn I've seen this elsewhere, but
I don't know. Was that what the original code was doing? In the red?
It was indeed, yes.
So
it's not a regression. In fact, this bit is not a regression either. But now we understand that it's a limitation.
Is that a memcopy thing? Does memcopy not take pointer to const? I can't believe that.
For the source, that's actually an interesting question. Let's see, CP reference memcopy. I know the C standard and const don't always work the way you would expect. Yeah, source is const.
It's right there like I'm expecting it to be.
Yeah, sounds fine. So why were we doing that? Were we assuming that they're the same type? It seems like it may
I
have just
have
been,
no
you know,
idea.
same pattern. This seems really familiar. It feels like I've looked at this before.
We're converting the first pointer to char pointer and the second one to const in both cases for the inputs and the outputs.
Yeah. I think we might have another case where we do cast everything to const char except for the output. Yeah, I first we return I first here.
Accidentally try and hit them.
Is that why is that? Eventually we need to rewrap. That's right. I believe the reason why we take the const away is so that when we finally return it, if the original source was const, that adds constness. Whereas if we put const here, if we tried to return and the original source was non-const, which is totally fine, that would implicitly attempt to remove constness. So to make the return work, that's why we need to.
Okay, because the return was implicitly converting.
Yeah,
and
this is from I first to init. And this is after we advance. What's it?
The old return. The old
return directly used I first cho. That's right.
There.
But now we
reinterpreting too.
Yeah, well now
but the
this
reinterpret would be casting
won't.
away
Yeah,
const,
it won't remove const.
Yeah. All right.
It won't remove const. So if we added const here, then this would try to be going from a const in star, say, reinterpret to, this would go from a const char star, reinterpret to like a modifiable in star. That would remove, so that's no good. So we do really need to remove here because we can always add constants back. Okay, so that explains both of these. These are good. It's only this one that needs to change. Okay, let me get that citation. Specialized algorithms general. You're so special and you're so general. 85. But what about general algorithms specialized? We need that stable name. Okay, let's see. Pre-existing issue that
it's not really pre-existing.
Is it? Oh,
because this wasn't. Oh wait, I take it back. This is pre-existing. We should have fixed this when we updated the old school stood algorithms.
Yeah. Could there be any other occurrences of this throughout the STL? Possibly this will show something.
We'll see the other one, right? There's another one,
only,
and we'll
only
get
two.
This review. So
okay. Facing Carter and noticed. On new working paper paste. Nope, wrong. This. Specifies, let me see if I get this right. Specifies, was it voidify in italics? In such a way that it can be called with pointers to const and will return non-const, return modifiable with star, allowing, let's see if I can describe this, const elements to be constructed in uninitialized memory. Accordingly, this reinterpret cast vol-char star should be like that to handle output iterators that are, or to handle outputs that are pointer to const. Okay, does this sound right? Pre-existing issue, the case I noticed, N485 specifies voidify in such a way it can be called with pointers to const and will return modifiable void star, allowing const elements to be constructed in uninitialized memory. Accordingly, this reinterpret cast volatile char star should be reinterpret cast const volatile char star to handle outputs that are pointer to const.
Looks good to me.
Cool. Thanks. Okay, so after converting all these from arbitrary contiguous iterators to raw pointers, and then converting these with interesting casts to pointers to characters named as ch, then we get the count of elements as the minimum of them. We get the count of bytes by subtracting the raw pointers to characters. So this does not do any division by constant, size of t. This is just directly subtracting the character pointers, which actually ends up being a little bit more efficient in CodeGen, and then gives that to memcopy. Being very careful here because we just fixed a bug where we were getting confused between count of elements and number of bytes. So this is a count of bytes, so this is good. And then previously we would just directly reinterpret back, but now we have to handle the arbitrary contiguous iterators. So that's what's going on here. I do see that there should be a new line here. Style, there should be a new line between non-chained if statements, because I like to see when we're taking a breath between one chain of if statements and the next. Otherwise, it all runs together. Okay, so if const expert, the init is a pointer, which is indeed our input type. Then we can just assign, and it's going to be take I first ch, which is the non-const char star, add back the number of bytes, and then reinterpret, potentially adding const to the init. Yep, that's good. Otherwise, okay, we need to use a plus equal because this is some arbitrary user-defined contiguous iterator. So we are going to take the same thing, the character pointer plus the number of bytes, but then reinterpret that to the pointer type with the correct element. So like int star. This is going to reinterpret to, this could potentially be top level const, but that's fine. That'll be ignored. It would be pointless to try to remove const there. And then once we've got a raw pointer, we still can't go back to the iterator type, but we can get a number of elements. So that would be this minus I first putter. Okay, so this is kind of elaborate. Is this better? This does a pointer subtraction, which I know I'm micro optimizing here. This does a pointer subtraction, which is going to divide by the size. We could just express this as plus equal count divided by size of value type. That would be less, it would make the line shorter, but it would also involve fewer transitions between the character pointer domain and the type pointer domain, and then the contiguous iterator or the subtraction. I think it would actually be simpler to just say plus equal count divided by size of t, because the size of t is implied either way. So it's not like that can be avoided. Yeah, and there's no more efficient way to get that.
Yeah. I think the shorter way to write it is clearer. And I didn't suggest that before because I wanted to avoid the division.
Yeah, but yeah, that division is sneaky. It's always in there.
You get the division anyway. I forget. The division's implicit when you subtract pointers.
It would be simpler to add count divided by size of what is that? Iter value? I don't know how to spell this.
Yeah, underscore capital.
20. We are 20 though, aren't we? We're in ranges. Do we have access to
additionally 20? Is this ranges?
GitHub claims it is.
It's got an in-out result return type. Yes, this is ranges.
Yep.
Okay. Yeah, we can use lowercase iter value t.
Okay. Iter value t of the init, better not be confused about that type. Yes, the division by size of is implied either way, and this avoids needing to jump between character pointers and element pointers. Okay, it'd be simpler to add count divided by size of iter value t init, because this is the init. Okay. Then we ask, is pointer out it? Seeing we're in interprecast here, we go to the correct type, and then seem suggested transformation. But let's make sure we get the out it. So I always say, novice copy paste code with no understanding of what they're doing, an expert copy paste code with full understanding of what they're doing. That's the out it. Right. I could phrase that as a suggestion, but I'll just leave it like this. Okay, similarly, yep, it's still count because the count is the same either way. Divide by the size of the iter value t of out it. Okay. Good. I didn't do anything horrible. I dropped that iter value t. Then when we're done, we can just return brace I first, O first. These were these top levels. They are parameters. I forget if we get implicit moves there. I think we do.
None of that usage. We could be moving those two.
I thought you get implicit moves from parameters, even though you won't get NRVO. Am I wrong?
If you return name a parameter, yes, you do. But that's not what's happening here, right?
It's got to be exactly the same type, but here we're actually constructing an in-out result.
Right. We're not returning parameter. We're constructing something from parameter.
Yeah. So that looks like it should be a move. Yeah. And this code is new, so it's not pre-existing. Okay. These can be moved. It would be slightly better to move these, as it won't happen. Okay. Okay, that was uninitialized or copy mem copy common. Let's go down. Okay, so now we're looking at uninitialized move unchecked. Okay, here we're just changing the criteria because we were already trying to call copy mem copy common. Previously, we asked, are the sentinel and the iterator types exactly the same? After ignoring any, yeah, we weren't getting the constants in there. Same with the output. And then, are you really trivial? Now we're going to handle sentinels that differ. So that's good. Increases consistency and generalizes the optimization. So we're going to ask, if const expr, we still need put or move cat, because this is a move algorithm, for it and out, if that's really trivial. And if C is a size sentinel for it and OC is a size sentinel for out, okay, that's good. We can just return copy mem copy common, and it can be mem copy because it's uninitialized. Give it I first, range is next, I first, I last. That could be a move. O first, range is next, O first, O last, and that could be a move too. Okay. Similarly, let's see, I last and O last would be non-const and moved from here. Okay. Okay, that's that algorithm. Great. Next up, we got 128 lines next till. Yeah, I thought I was almost done. And then we got a little bit of test code. Okay. Hopefully this should be a little bit faster. This looks like actually some code is being moved around here. Yes. Okay. So we got some code being moved around. We had just reviewed this. This looks like it's moving up even higher. I'm trying to remember because I had when I merged Adam's last PR with main, I had to move this around. I think I had to move it to a whole different file. I had to move it to xutility, I believe. And I had to choose a location for it. I ended up putting it here. I think I had initially tried to put it up too high. And I didn't have something. Maybe I'm thinking of something else. This doesn't really have a lot of dependencies. Okay, so because we see a code move, the thing I'm always paranoid about is if unintentional edits are happening. One of the dangers of moving code around is it's tempting to like resolve a merge conflict if changes are coming down from main. Like, oh, I just deleted that code, and you don't realize you actually moved it, and then you end up losing edits that were made somewhere else. So let's see if I can get this here. Okay, this is the old code. Let's go up. New code. It's like the one thing I missed from our internal diff tool is showing moves. It doesn't show this anymore in the Explorer, but it can be turned on so you can compare selected. Okay, there are no differences. That's what I like to see. Great. Okay, so everything at the top xutility is good. We just moved it up above copy. Okay, now we are, it looks like this is a move upwards of move cat below copy or above copycat. And that's why this diff looks just absolutely wretched. And then it's going to, as the comment said, it's going to detect move iterators here, and then, yeah. Okay. Wow, this diff is just absolutely terrible. I'll just review it as new code. So, note, pointer is not a contiguous iterator if it points to volatile type. Okay, that's a property of the concept. Pointer move cat is templated on the source, the dest, and we've got a non-contiguous bool that says if the iterators are not both contiguous, source and dest. Okay. So if they're not both contiguous, then definitely no. It is false. We have this dedicated false copycat because we have so many different kinds of categories, and it's somewhere up there. Oh, here it is. Yeah, really trivial false and trivially copyable false. Okay, then footer move cat. Okay, Adam is following the convention that we like the primary template to be for when the bool is true. So there is some negation in non-contiguous there, but otherwise the convention is being followed. So I'm happy with that.
So funny story. He wasn't originally following that convention, and I pointed out in my review. I was like, normally, when we have a bool parameter that's used to select specializations, we have the primary template be the true case. And so he changed it from R contiguous equals blah, blah, blah to just non-contiguous and put a not in front of the condition instead of going to the trouble of changing the bodies of the two specializations. So it's sort of weird that we have this condition that's a negation. Yeah. But I didn't have it in me to ask him to change it again. So
yeah, agreed. Yeah.
You can if you want.
It ends up being fine. Because like we just introduced the hey, stuff is bad case first, and that's actually true for a lot of type traits. Like usually the type trait that absorbs the infinite universe of stuff that isn't eligible for the optimization comes first. So it's a little weird, but I think it's acceptable. Okay, so we've got the primary template followed by these specializations for false. We've got putter move cat. And then if is trivially assignable. Now since we're dealing with not just raw pointers, we need to use the type traits that deal with arbitrary iterators. So that's what is happening here. If the iterref type of dest and then iterref type of source but here he's removing reference. That's because this is put or move cat. So we need, if we pass like int ref that asks, what if we assigned an L value int to something? If we pass int that asks, what if we assigned an R value int or string or whatever? It would matter for string. And it could matter for int too, but would matter more for string. So that's what the remove reference T is there for. That's move, so that's good. It just looks horrible because we're diffing against copycat. Okay, so iteref, remove reference on the source for move. And then if that's true, put or cat helper, give it the value T of the source and the value T of dest, rather than just removing the pointer. So that's good. Otherwise, false copycat. Okay, good. And here, because this machinery is defined all the way down to CS+ 14, we need to use the ugly form of iter value T, which will fall back to classic iterator traits. Then the put or move cat of, if we've got a move iterator for anything to any kind of dest, and the iterators are not otherwise contiguous. Oh, because move iterator, does move iterator qualify as a contiguous iterator? I'm guessing it doesn't, because it does that weird.
It does not satisfy the concept, no.
Yeah. Okay.
Because
so
its reference type is not an L value reference.
Okay. Thanks.
So it's technically not equivalent if to just convert it to a pointer and operate on the pointer, unless you're also moving, right? If you convert it to pointer and you do the move, then you're great. But
yeah, explicitly, yeah. Okay, so this is saying if the source iterator is a move iterator and you have any destination, then the move iterator is going to disqualify it. So non-contiguous is true. But hey, let's just remove that move iterator and ask the question again, and then redetermine whether the unwrapped move iterator is contiguous. This is good. This could though punch through and say : oh, we don't actually have a type. These are just bools. We can't punch through. This doesn't have a self-type def. Here I'm referring to the idea of, instead of creating a chain of base classes for type traits, you can, what I think of as punch through and get the most derived or the most base type, like integral constant, and use that directly as your base class. So you just have your type trait derived directly from true type or false type. We can do that, and this is potentially a throughput improvement because you end up with simpler layout, and specializing class is one of the most expensive things we can do, as I understand it. We can do that with the standard type traits because they've got this self-type def. Let me see if I can show you that. Helper classes. Yeah. So if your type ends up deriving from an integral constant, then if you ask its : type, that is a type def for itself. So as long as this is your only base class, no matter how far up, if you ask : type, you smash it down to either true type or false type if it's a bool constant. We use this occasionally in the STL when we're working with type traits, but here it's not applicable and it's not really going to save bunch of throughputs. That's good. Okay, so that handles move iterator. Now we're on to copycat. They're actually named cat, but there is no cat implied. Bool non-contiguous is not iterators are contiguous source dest. Yep, put her copycat, it's false. For arbitrary source, arbitrary dest, if you are contiguous, then ask itereft dest, itereft source. Here we directly use itereft because we're answering the question, hey, what if we used an L value as the source? Then put or cat helper, give the value types the iterators. Yep. And then otherwise false. Okay, good. And then what about move iterators? For arbitrary source and dest, if we have a move iterator of any source and a dest, and you're not contiguous, then here, and this was called out in Adam's summary, ask the put or move cat, because the move iterator is going to move of source and dest. Okay, that's all good. Next up, implement copy mem move. Looks like this is potentially, is this potentially the same issue? Was the other one a copy, mem copy? That was in what, XMemory? Copy, mem copy common. Yeah, I believe it. I believe it's also affected. Man, that voidify is weird. Okay, so where are we? Copy mem move. So we have template on class contig it, class out contig it. Copy mem move returns one of those and takes first, last, and then the out dest. Okay. We're going to convert each of these to pointer form, and then we're going to do the cast. So here, the source, you apply CV and then remove the V, and then you get const char star const. Okay. For the des, it looks like this should be const volatile char star to handle the voidify and then remove.
I agree.
Yeah. Okay. Thanks, Casey. We believe this should also be reinterpret cast of const to handle the star backtick voidify backtick star wording. Yep. And then remove that because we actually do need to scribble into descha. Count the characters, call the mem move, form the return type. If the out contigate is a pointer, then we can just take the character pointer, which is a plain char star, add count number of bytes, and then reinterpret to the desired type, which will potentially add constants. Agreed? Otherwise, we're going to take that dest iterator, and we're going to add, okay, here there's just no division. We just got the pointers to subtract last minus first. Yeah, that's good enough. That'll do the division implicitly. It might save like a cycle or two to say count divide by size of, but not going to ask for that. Question, does that need to be a move? Or could it be a move? It could be. We're not directly returning it. We are doing operator plus though. But that could also be move enhanced. Seems very, very unlikely. I don't think it's worth, kind of don't think it's worth asking for a move there. Yeah, somebody can do it later. Okay, so copy backward. We've got generalizing to, here we had followed this sort of weird convention where we would just repeat the template parameters for overloads even as we gained knowledge about what they are. We've sort of moved away from that convention, so that's why these parameters are becoming more specific. This thing always required contiguous iterators. In fact, they required unwrapped raw pointers. Now it's accepting contiguous iterators. So template contigate 1, contigate 2. Yep, that's all good. Implement copy backward like function as mem move. That's still accurate. So we're going to to address everything. We are going to reinterpret. Yep. I believe we've got the same issue here. I'm going to call them out individually rather than just saying audit, because each of these cases is a little different in the context. Again here, the des putter, yep, apply the constants, remove it, okay. And then we used to just directly static cast back, and now we can't do that, so auto underscore result is C STL mem move. If contigate 2, which is the output, is a pointer, then we can just take result, and result is a void star. So that's why we can static cast back to the original type. Otherwise, we can't do that. We've got to take the original dest and then advance it. Yes, the static cast here is correct. Because that's what we were doing before. The thing that just jumped into my brain was, some of the CRT functions are kind of weird in that they return the source pointer rather than the last pointer, basically. Yeah, I'm going to double check. I'm a little bit worried the code might be wrong. Was that CP reference mem move? Can't remember which function does that. Then there's the functions that return null when they don't find something, which is different than STL semantics. Oh, hello. This is the function I remember. This returns dest. The original, the non-incremented source. Is that what this is supposed to return? Oh yeah, because this is copy backward mem move. We want to pretend that we're mem move. Okay, so we're following its bizarre convention. And then callers of copy backward mem move, I can't remember if they're here, but I can do a search. Those will adapt to the STL convention when necessary. So there's no error here. Stuff. Oh, this must be, oh, I'm in the chart repo. I was like, there's no occurrences here. You're in the wrong repo, STL. There we go. So what do we got? This is not adapting to STL semantics. What are we doing?
Move backward returns the beginning of the output range.
Oh, because it's backwards.
Yeah.
Yeah.
Because it's bizarre in every way compared to every other
algorithm. I forgot about that. We're reversing. If this were plain mem move, then okay.
Yeah, you tell it the beginning and end of the input range and the end of the output range, and it tells you what the beginning of the output range is.
Yeah. So here the CRT semantics are actually what we want. Surprise. Okay, so that's cool. Thanks, Casey. Okay, so yeah, we were just directly casting. Now we can cast here. That's good. Otherwise, we need to synthesize the return value. So we get the dest, which is the end, and then we subtract the right number of elements, which is last putter minus first putter. Okay, that's looking good. And we've got code coverage, I believe, to check those return values.
We could also recommend changing that to count divided by size of.
Yeah, we could.
If we want it to be consistent with the other function.
Yeah, in this case, though, we've got the pointers right here.
True.
And this reads naturally. Having to form size of iter value t is kind of annoying. I think this is fine. This will boil down to basically the same code gen.
Okay.
Yeah, there's a slight consistency, but on the other hand, like we subtract for n very commonly too. So yeah, I think I'll let it go unmarked. If you want to add a comment though, if you really care, I guess you can. Okay, we had checked the move here. Yep, that's all good. Okay, finally done with X utility. And now test compile. Okay, so this was testing some volatile stuff. That's being removed. Because we now say that volatile iterators are not contiguous. So what was this doing anymore? Last time this said volatile.
We were supporting volatile before.
Yeah, and now we're saying
the standard says that volatile things are sometimes trivially copyable, but it's wrong and it shouldn't say that.
Yeah. Yeah,
because volatile is a declaration by the programmer that the order and size of memory accesses is important. So we shouldn't be converting them into byte accesses behind their back.
Yep, agreed. Okay, so this is.
I was pretty sure you agreed with that when I told him to just go ahead and rip out the volatile support.
Yeah. So this is actually great. So this is being ripped out. Let's just make sure that no comments need to be changed. Okay. Yep. Okay, we've still got coverage that const dest will not handle. Okay. Now this getting rid of the comment, valid anywhere should go trivial. Yep, okay, so that just all vanishes. Great. Anything else need to change? No. Okay. And then infallible. That's so weird. Okay, so that is, we're just not passing anything there. Okay, so that's good. Okay, so the one thing as I reach the end of this review that I'm wondering is, should we have test coverage for that weird voidify stuff that we just realized?
Yes. Given
Yeah.
how weird it is and the fact that we actually found bugs.
Yep.
During this review
Okay.
that would have been caught by such test coverage, then yeah, we should ask for test coverage.
Okay, let me find where we mentioned
And
that.
now I'm concerned that putter copycat and putter movecat might need to be fixed as well.
That's a good point, because we had never contemplated that the dest might be const.
Right.
In fact, we were probably pretty strict about, hey, if that dest is const, it's not going to compile, so we should not reroute to memcopy. Okay, I can add maybe just another comment on the same line. Sure. Because I'll need to be resolved separately. We should also have test coverage for all of the we'll say algorithms that are affected by this star back voidify issue. Casey notes that putter copy cat, putter move cat might also need to be changed, as we previously never expected to be able to handle outputs that are iterator to const. Okay. I wonder if we would need, do we need to worry about permitting stuff in the uninitialized algorithms that don't go through the voidify code path? Because I think voidify is only used for the weird uninitialized algorithms. Is that right?
Correct.
Yeah.
Okay,
These
so
are the
that
only
is
algorithms that take pointers and or pointer-like things that don't actually denote objects, but they denote storage for objects. And the pointy type is only important because it tells the algorithm what kind of objects you want it to create there. They're very weird.
So should I mention we should ensure that only the uninitialized meow algorithms permit pointer or iterator to const, and that this does not accidentally extend to plain meow?
Yes.
Okay.
Which might mean splitting those traits into two and having one do the assignment check and one not do the assignment check.
Yeah, you know what? This is sort of growing beyond the original scope. I wonder if we should file an issue for this.
That would
clean
be
it up.
okay.
Yeah. For this PR alone, it seems like just changing the const volatiles seems reasonable, and then we have the follow-up issue, or should we just not comment on the const volatiles now? Because it is pre-existing.
The const volatiles it's just adding a const. I'm not concerned about making that change now.
Okay.
And
okay, cool.
maybe leaving things in an inconsistent state until we follow up later.
Okay, so I will move that. I hadn't mentioned test coverage or anything. Okay, cool. So I will submit these comments as is, and then I can create a follow-up issue citing this and then saying we need test coverage. We need to make sure that it works for all the uninitialized meow, but none of the meow, and potentially, larger refactoring there. Okay, cool. So I think that's good. I am indeed requesting changes. Okay. Cool. And why don't we write that follow-up issue? It's fresh in my brain. Okay, so this would be bug. These are our labels. This is in memory because it's uninitialized. So uninitialized meow should handle voidify wording. And the citation is here. Didn't need all that. We use our cool auto links 4885 to make that into a link. Specialized algorithms general /4. Says that the uninitialized meow family of algorithms is powered by an exposition only voidify helper, which has the interesting ability to interesting property of returning modifiable void star. Surprisingly, this intentionally handles outputs that, or say output iterators that are, I don't want to say output iterator because I mean iterator used as output, not specifically the strength. Specifically, this intentionally handles destinations that are iterator to const, allowing const elements to be constructed in uninitialized memory. We should add test coverage for this scenario for all of the uninitialized meow algorithms that are affected. This may require reworking internal machinery like putter copy cat, putter move cat. Finally, we should ensure that we don't disrupt the plain meow algorithms, which should not be allowed to modify through iterator to const, as they aren't specified with voidify. And I can cite the PR 1772. Noticed while reviewing 1772, but filed as a separate issue as this is pre-existing and largely unrelated. Not trivial.
Pre-existing and non-trivial. Yeah, we didn't want to grow the scope of the PR.
PR's scope. Okay. So it's a bug. GitHub titles now respect backticks, which is pretty great. And we're like 485 says the uninitialized meow family algorithms is powered by voidify helper. It intentionally handles destinations that iterator to const. We should add test coverage. This may require working internal machinery. We don't disrupt the meow algorithms. We should not be allowed to modify through iterator to const. I've got the citation correct. Yes, great. Okay, 1780 filed, and the backtick's like, oh, but we don't get the stars. Lame. Okay. I'll get rid of this. Probably there's too many stars in titles. Okay, better. And there we go. Got all the comments. It is change requested. Okay, I think that's it for this video code review. Does anyone have any questions for the various topics we talked about?
I would scroll back through the chat and see if anybody had questions. My cat's in the way.
Wait, let me turn on my incoming video. I can see the cat. Okay.
You can't. Yeah. She's invisible. Where cat? Now I can see. Nope. It looks like only I had comments.
Okay. Cool. Well, yeah, if anybody has comments about, the type trait optimizations we have or whatever, just let us know. We're always happy to answer. Okay, I think we can stop the recording. Thanks, everyone.